Okay, so what we've talked about to this point is the idea of forming Lewis dot, writing Lewis dot structures, and then figuring out the geometry of the molecule. Now we are on our way towards intermolecular forces, but I want to talk a little bit more about the bond formation process and review hybridization, or for some of you, this may be kind of a new topic, so that we're all at the same place at the end of this. And hybridization is going to be our first introduction really to an organic chemistry topic. So in terms of forming a bond, there are different levels that we can look at bond formation of. So we could look, for instance, at taking a Lewis dot structure and simply saying, okay, I'm sharing these two electrons in order to form a single bond. Now, what does that mean at the atomic level? Well, remember that a nucleus is positively charged, and these two hydrogen atoms would have a nucleus surrounded by one electron. And when you bring those two hydrogen atoms together, the way you form the chemical bond is by the electrons being simultaneously attracted to both of the nuclei. In this case, these would be hydrogen nuclei. And so, in this case, that's the sharing of electrons. At the atomic level is a simultaneous attraction of the electrons to both positive nuclei. Now, there is a higher level at which we can look at bonding, and that is to look at the overlap of orbitals. And so in general chemistry, you talked about, for instance, s and p and d orbitals. And those orbitals are basically mathematical descriptions of how electrons move as they are going around the nucleus. And instead of looking at the mathematics of that, what we do is we tend to look at shapes. And the shape is just simply the probability of finding the electron at any point around that nucleus. So when we say that a hydrogen has a 1s orbital, the s stands for spherical, and the 1 is the shell number, or the principal quantum number as to the row number on the periodic table. And this 1 represents that those electrons are relatively close to the nucleus, as opposed to if it was a 2 or a 3. So S stands for spherical. We'll see what p orbitals look like in a minute, or review that. So the idea of forming a hydrogen molecule then in the orbital view is to overlap those two orbitals, those two mathematical descriptions, in order to form then the single bond. And the orbitals can either be viewed as waves or particles. So if they were looked at as waves, you might look at that in a physics sense as, okay, here is a simple wave, and then here is another wave. And so I'm going to go ahead and add those two up mathematically to get, the corresponding sum of those two. And that's an oversimplification of the orbital picture, but that's what we're going to do, is we're going to overlap those two. In essence, we're going to overlap those two spheres to form the sigma bond, to form the single bond, which I will call sigma bond in a moment. So just to review, s orbitals are spherical. The principal quantum number 1 is the row number on the periodic table. 1 says electrons are closer to the nucleus than 2 or 3. As the principal quantum number gets bigger, the position of the valence electrons increases away from the nucleus. P orbitals, there are 3 degenerate p orbitals, and what I mean by that is that they have the same energy. The p orbitals, basically there is an x, y, and z orientation of those, where the electron spends 50% of its time in this sphere, or in this dumbbell shape, the other 50% of its time here, and there is a nodal plane here, and that nodal plane is where you have 0 probability of finding the electron, and it's quantum mechanics that tells us how you get the electron from this position to this position and never stop there, but that's beyond the scope of this class. But there are 3p orbitals, x, y, and z. Of course, real life reality, there is no x, y, and z orientations. You can't look and go, oh, that's the x-axis. So the idea is that they are basically perpendicular or orthogonal to each other. And we'll talk about those shapes, and we're going to mix those shapes to form hybrid orbitals. So when we overlap two orbitals, as I said, we're basically overlapping the waves in order to form a single bond. And that's what happens in hydrogen, so that the resulting bond, there is a probability, again, of finding those electrons between those two nuclei. So what we're going to do is we're going to talk about how carbon can form different hybrid orbitals. And we're going to talk about this first with methane. So methane is CH4. It has a carbon with 4 hydrogens attached to it. Those 4 hydrogens are in a tetrahedral geometry. That's what we get from the Vesper theory. And what people knew early on was that all 4 of the carbon-hydrogen bonds in methane were equivalent. So any hybridization of carbon in this case has to give that result, that all 4 CH bonds are identical to each other. And the way we start with hybridization is we're going to start in the ground state of carbon. Now, the first complication that people had to come up with or had to solve in coming up with hybridization for methane is the fact that in the ground state of methane, you have 1s2, 2s2, and 2p2. And remember that when you're drawing out the ground state electronic configuration of atoms, you always fill each orbital up with 2 electrons before you can move to the next higher orbital. The p orbitals have the same energy, which the term is called degenerate. So you have to fill the 2s orbital before you get to the 2p's. Now, the valence electrons are only those electrons that are in the highest principal quantum number orbitals. So in this case, we don't use the 1s orbitals to bond. We only use the 2s and 2p orbitals to bond. So the first problem is methane has a CH4. It forms 4 bonds to carbon forms 4 bonds to hydrogen. Now, if carbon had this ground state electronic configuration, why wouldn't we write carbon like that, with the pair in the 2s and then 1 each in the 2p orbitals? That means that carbon could only form 2 CH bonds. So the first thing that we have to overcome is that issue. And what we say is that in this case, we're going to apply a little bit of energy, and we're going to promote this 2s, one of the 2s or electrons, up to the empty 2p orbital. So now if I do that, I'm now going to end up with 4 unpaired electrons, which would give carbon this electronic configuration, or this Lewis dot structure. It would give it 4 unpaired electrons that it could now go ahead and share with the 1s electron of each of the 4 hydrogens. So that the excited state of carbon is what is used to bond hydrogens in methane. Now, in chemistry, energy is the currency by which we find out whether reactions occur or not. I usually at this point say, in politics they say follow the money. In chemistry we follow the energy. So where does this energy come from? And it's kind of a chicken and egg question, but the energy comes from the fact that I'll be able to form 4 CH bonds, which will overall make that molecule far more stable than just CH2. There's another complication here. And that is that as I overlap the 2s orbital and the 3 2p orbitals, the s orbital being spherical and each of the p orbitals being, dumbbell shaped, and I'm writing them all together here, as we overlap those two orbitals with the 1s orbital of hydrogen, wouldn't we expect that if we overlap two spherical orbitals, or if we overlapped a p orbital and a spherical orbital, would we not expect to get different bonds? And the answer is yes, we would. But I told you earlier that methane is known, and as a fact, has all 4 bonds being exactly the same. So now we have another problem that we have to solve. And the way we solve it is that what we say is that we're going to mix the s and p orbitals together. We're going to hybridize them to form 4 equivalent hybrid orbitals, which we're going to call sp3 orbitals, s plus 3 p's. And so if we have 4 equivalent sp3 orbitals, then as each one of those bonds the hydrogens, or is used to bond to form the carbon-hydrogen bond, now all 4 bonds in methane will be exactly the same. So what happens is we form these hybrid orbitals, and that's the reason why methane has 4 identical CH bonds. So we went to the excited state to get 4 unpaired electrons, and we now hybridize those orbitals to get 4 equivalent carbon-hydrogen bonds. Now, what's driving this process? And here's what's driving this process. When you take a spherical orbital and 3 p orbitals and mix them together, you get 4 sp3 hybrid orbitals. And the mathematics of this is that you get a much larger orbital on one side and a smaller orbital on another. And so these 4 sp3 hybrid orbitals have more electron density in the larger orbital. And so now when you take one of those sp3 hybrid orbitals and you overlap it with a 1s orbital, or even if you overlap these together, which we'll see in a moment, when you overlap the sp3 orbital with a 1s, you're now overlapping a bigger orbital with more electron density, and so therefore you're going to get a stronger bond. So again, where's the energy payoff in this? The energy payoff is you're going to get a stronger CH bond. The alternative would be to mix a 50-50 p orbital with an s orbital, and in this case, only 50% of the electron density would be in that lobe of the p orbital. So in this case, it's much higher, so we get a stronger bond. So 4 sp3 hybrid orbitals, what kind of geometry would that give us? Well, we've got 4 clouds of electron density. That means around the carbon, we would have 1, 2, 3, and 4 hybrid orbitals. So it's going to be tetrahedral according to our Vesper theory. We can see that a little bit better in the next slides. There's our tetrahedron. What we're missing is the little teeny tiny orbitals that are on the other side. There's 4 of them. And we can actually see those here in this tetrahedron. So 4 hybrid orbitals, tetrahedral geometry, perfectly consistent with Vesper theory. And then that's the structure of methane. So along the way then, as people developed this hybridization model, they had to reconcile some of the physical properties and what you knew about methane with what ultimately we accept as the bonding for this molecule. Now, is that the only way we can mix orbitals? No. Let's say we wanted to mix 2 of the p orbitals with the s and leave another p unhybridized. Well, then what I'm going to get is I'm going to get, if I mix two p orbitals with one s orbital, I'm going to get three sp2 orbitals, hybrid orbitals. Now, three orbitals would mean a trigonal planar geometry. And we can see that here. These shaded orbitals are the hybrid orbitals. So we get three trigonal planar sp2 hybrid orbitals. And then the unhybridized p orbital, this is left what we would call unhybridized. The unhybridized orbital will end up perpendicular to those three orbitals. It looks like it's trigonal bipyramidal, but it's not. Because trigonal bipyramidal would mean 5 hybridized orbitals. And in this case, I only have 3 and 1 unhybridized. Now, if you remember in the last video, I said don't ever bond carbon to 5 things, because that's that's mistake number 2 in organic chemistry. If you're going, but carbon's going to bond to 5 things. No. There's 1 electron in each of these 2 lobes. It's going to spend 50% of its time in the top lobe, 50% of its time in the bottom lobe. So carbon will still only be able to form 4 bonds. This is the basis, sp2 hybridization, of how we form double bonds. So what we're going to do is we're going to take, and let's say that we had this as our structure. Let's say we had hydrogen, carbon, hydrogen, double bonded. So this molecule is called ethene or ethylene. What's the bonding in this? Well, the bonding in this is that this carbon, each of these 2 carbons is sp2 hybridized. So that means that the carbon's going to have our 3 sp2 hybrid orbitals. Each of those contains 1 electron each. And there's going to be 1 electron in the unhybridized p. 1 electron here and 1 electron in each of the 3. So now what I'm going to do in order to form the carbon-carbon single bond is I'm going to overlap head-to-head the 2 sp2 hybrid orbitals. And this gets us to what is a sigma bond. And a sigma bond is when you take 2 orbitals, and they don't have to be hybrid orbitals, but when you take 2 orbitals and you overlap them head to head, then you end up with a sigma bond. This is also then what we call a single bond. So the sigma bond is going to be formed from these 2 carbons sharing electrons, but we're looking at it in a deeper angle of overlapping the 2 orbitals. And the carbon hydrogens then are overlapping the 1s orbital and the sp2 hybrid orbital. So we've got a sigma bond here, a sigma bond there. We're going to form a sigma bond, carbon-carbon bond, another sigma bond, and another sigma bond. And at this point, I'm going to take a step back and just say that when you have a spherical orbital like the 1s, 1s always can only form sigma bonds because you can't overlap a spherical orbital any other way but head-to-head. Okay? So I'm going to form those sigma bonds. Now, at this point, the Lewis dot structure for this molecule would look like this. And each of the carbons would then have an unpaired electron in the p orbital. In the Lewis dot structure, what we would do is we would pair those up to form the double bond. How does that work with the orbital picture? In the orbital picture, I'm going to overlap these 2 p orbitals sideways. I'm going to do a sideways overlap. and that is what we call a pi bond. So a pi bond is when we overlap p orbitals sideways. And that forms, in essence, the double bond. So now I'm going to overlap those to form the pi bond. And that's what we'll see in the next slide. So I overlap those two orbitals and I make the pi bond. Now a pi bond, in this case the pi bond, is both of these orbitals combined. A couple of ways you can look at the pi bond. In this drawing, it's kind of the two hot dogs lying above the sigma bond. Actually, they're not hot dog shaped, they're more mushroomy shaped if you do some calculations. So either way, these two things together, these two lobes, contain two electrons, and those are the pi bonds. Now the pi bond actually has this plane in the carbon-carbon double bond. That plane is a nodal plane, so the electrons again somehow pass from here to here without ever stopping there. That's quantum mechanics beyond the scope of this class. So that's what a pi bond looks like. And just another view of that with both lobes of the pi bond, the sigma bond, and then the carbon-hydrogen sigma bonds. Okay, so another view showing the planarity of the trigonal planar geometry of the carbon-carbon and the carbon-hydrogen bonds. How else can we mix? We can mix S and a P and leave two p orbitals unhybridized. So if we do that, again, we mix an S and a P, we get two sp hybrid orbitals. The Vesper geometry would say two lobes of electron density. They have to be 180 degrees away from each other. And that's what we see up here. We see those 180 degree sp hybrid orbitals. Each one of those contains one electron. We have two unhybridized. We now have two unhybridized p orbitals. Each one of those contains one electron. And they are, again, in their normal orthogonal or perpendicular position. So this is an example of an sp hybridized carbon. Sp hybridized carbons are what we can use to form a carbon-carbon triple bond. So for instance, if I was looking at a carbon-carbon triple bond as a Lewis dot structure, it would start out like this. How did I form this single bond? I overlapped these two sp hybrid orbitals. I overlapped those to form the sigma bond. I overlapped the sp hybrid orbital of carbon with the 1s orbital of hydrogen to form the second and third sigma bonds. So I would have a sigma bond, another sigma bond, and the third sigma bond. That leaves these two p orbitals in each of the two carbons that will need to overlap sideways. So instead of forming just one pi bond, I'm going to form two. So I'm going to overlap these two in order to form the pi bond. And so that's what I do. Again, one electron in each, overlapping sideways to form the two pi bonds. So one pi bond would be above and below the plane, and the other pi bond would be in front and in the back. And again, both lobes make up a pi bond. So in a carbon-carbon triple bond, you end up with two pi bonds, or four, basically a pair of these hot dogs is one pi bond. It gets a little more complicated in the actual calculation. It looks like a magic wand sitting inside the middle of a donut, which means these electrons basically can circulate all around. So this is how we form the basics of sp, sp2, and sp3 hybridization. And this is how carbon bonds, either by a single bond a double bond, or a triple bond. So here's just a few more views. That carbon, this molecule of a carbon hydrogen triple bond, that's called acetylene, or it's also called ethine. And so it would look like this in terms of its sigma and pi bonding. And again, it would be linear. If I can't see the pi electrons, it would look like that. Okay, so now the question becomes, what about the hybridization of non-carbon atoms? Or what is the hybridization of carbon atoms? How do I go about determining the hybridization? How do I draw out the structure and sketch what I call a hybrid, what's called an orbital picture? And so here's how we do that. Let's take, for instance, a hydrogen attached to a carbon double bonded to an oxygen. And this molecule is called formaldehyde. Typically, formaldehyde has dead things in it. Well, actually, dead things are in formaldehyde. So formaldehyde would have this structure. Now, in order for me to sketch what the orbital picture of this looks like, I need to know what the hybridization of the atoms are. And let's talk about the general way to do that. So here's what we know. If I asked you and said, for formaldehyde, go back to the VSEPR rules, what would be the Vesper geometry of this carbon? And, well, we'll leave it at that for the moment. So the video is going to stop, and you're going to choose what would be the Vesper geometry of that carbon. Okay, hopefully you did that. What is it? Well, we would basically say we've got one pair here, one pair of electrons here. A double bond is treated as if it was a single pair of electrons. I have 3 pairs of electrons around that carbon. What does that mean? That means it is trigonal planar. Okay. Now, what's the hybridization of that carbon? Well, here's how we can relate Vesper geometry through the electron pair geometry into hybridization. And let's create a table for that. So if you had, in our case, of the acetylene molecule that we just looked at, I would have this carbon having how many pairs of electrons? And I'm going to put that in quotes because, again, we're going to treat the multiple bond as if it was a single pair. How many pairs of electrons surround this carbon atom? 2. What is the geometry of that carbon atom? It's linear. What would be the hybridization of that carbon atom? It would be sp, as we've already seen. Okay, now let's go to 3 pairs of electrons around a central atom like we have up here. We've already said that's trigonal planar. And now the question is, what is the geometry of that? Well, in our trigonal planar geometry, what we had was we have 3 hybrid orbitals. And at this point, let me make something absolutely clear. The hybridization basically is the number of hybrid orbitals. which is also equal to the number of sigma bonds. So when you have two pairs of electron density around a central atom, in essence, what we're saying is we're treating this multiple bond as if it was a single pair. What am I counting? I'm really counting the number of hybrid orbitals. So when you have two hybrid orbitals or two sigma bonds, you have an sp geometry. That's linear geometry, which we're counting as two electron pairs. In an sp in a trigonal planar geometry, how many hybrid orbitals do we have? We have 3 hybrid orbitals. 3 hybrid orbitals means what geometry? sp2. S and 2 p's. Okay? So what if we had 4 electron pairs around our central atom, like we did for methane? How many hybrid orbitals did we have? How many sigma bonds did we have? We had 4. What was the hybridization? sp3. What's the geometry? Tetrahedral. So in this case, we can relate Vesper theory to hybridization by counting up the number of hybrid orbitals or sigma bonds. And so that will give us the hybridization, which would also then give us the geometry, which we get from our Vesper in terms of our VS-EPR way that we determine that geometry. The only thing I need to add to this chart is that the hybrid orbitals, the only thing that can go into a hybrid orbital is either an unpaired electron that is used to form a sigma bond, or also what can go into a hybrid orbital are the lone pairs. So lone pairs can only go into the hybrid orbitals. So what that means is that the number of hybrid orbitals around a central atom is equal to the number of sigma bonds that atom is involved with plus the number of lone pairs. And that will be true for any atom. It's true for this carbon. How many sigma bonds does this carbon have? 1, 2, 3. It's sp2 because it doesn't have any lone pairs. Now, what about this oxygen? What is the hybridization of this oxygen given this formula? Okay, video is going to stop and you're going to choose the correct hybridization. All right, hopefully you chose the fact that it has 1 sigma bond and 2 lone pairs. That means it has 3 hybrid orbitals, which would make it sp2 hybridized. So what's that oxygen's geometry? It is also trigonal planar. Okay. So now we have to sketch this. We have to sketch this out. So let's go back, or let's go to a blank slide here, and let's go ahead and do that. So I'm just going to rewrite my molecule to reorient myself. The first question I will always ask you when sketching an orbital diagram is what's the hybridization of the non-hydrogen atoms? And in this case, you would say this is sp2, and this one is sp2. How did I get that? Number of sigma bonds plus number of lone pairs gives me the number of hybrid orbitals, which gives me the hybridization. sp2 means that the number of hybrid orbitals is 3. Now, in order to sketch this picture out, I need another mini chart. And the mini chart is going to be this, that if you have any atom that's sp hybridized, it will have 2 hybrid sp hybrid orbitals, and then it will have 2 unhybridized p orbitals. The number of electrons that go into these orbitals is going to depend on the atom. So in general, what we do is we hybridize orbitals, and then we put the electrons into them. So what would an sp2 atom look like? It would have X, it would have 3 hybrid orbitals in a trigonal planar geometry, and then it would have an unhybridized p. Number of atoms that go, or number of electrons that go in there is going to depend on the atom. And then finally, what would we have if we had an sp3? We would have 4 hybrid orbitals and all 4 of those would be sp3 hybrid orbitals. What would the geometry be? Tetrahedral, trigonal planar, and overall linear. So with these diagrams then, and figuring out what the hybridization is, we can sketch the orbital picture. So in this case, we have 2 sp2 hybridized carbon, a carbon and an oxygen. So let me draw my carbon, let me draw my oxygen. We form sigma bonds from the hybrid orbitals. So here are my 2 hybrid sp2 hybrid orbitals. Oxygen would then have 2 hybrid orbitals here. Carbon over here would have 2 hybrid orbitals. So those are all the sp2 hybrid orbitals. Each carbon and oxygen atom are going to have 1 unhybridized p. The way I've drawn this, the carbon's attached to 2 other hydrogens, so that means over here 2 of the sp2 hybrid orbitals are going to be overlapping the 1s orbitals of the hydrogen to form these 2 carbon-hydrogen bonds. Okay. Now let's put in the number of electrons. For carbon, it has 1 electron in each of the hybrid orbitals and 1 in the unhybridized p. And then hydrogen, of course, in its 1s has 1 1s orbital. Now for oxygen, oxygen is going to, because oxygen has 2 lone pairs and 2 unpaired electrons, so the rule is that the lone pairs can only go in the hybrid orbitals. So that means that these 2 lone pairs have to go into these 2 sp2 hybrid orbitals, and then the 2 unpaired electrons, one will go in the p orbital and one will go in the sp2 orbital of the oxygen. So the rule is that the lone pairs can only go into hybrid orbitals. They can never go into a p orbital. And so now what I have is, now I have a carbon, oxygen, each sp2 hybridized, now containing the correct number of electrons that we would transfer from the Lewis dot structure, from the Lewis dot structure of the atom into this orbital picture. The hydrogens then, of course, would be forming one set of sigma bonds, which we would have here, We would have those two sigma bonds. We would form a sigma bond between the carbon and oxygen, which would be the overlap of those two sp2 hybrid orbitals and the sharing of those two unpaired electrons. And then in order to form the pi bond here, we would sideways overlap the p orbitals to form the pi bond. And so this would be what I call an orbital diagram or an orbital picture of that formaldehyde molecule, showing how we form the sigma and pi bonds from the particular orbitals. So the way to do this is to first of all identify the hybridizations of the atoms, the non-hydrogen atoms, sketch out their pictures, orbital pictures, which you get from this diagram. And again, that diagram doesn't have any electrons in it. Place the electrons in the orbital by transposing the Lewis dot structure into the orbital picture, and then finally forming your sigma and pi bonds by overlapping. Remembering that lone pairs can only go into hybrid orbitals. And that is why that's why over here, when I said the number of hybrid orbitals equals the number of sigma bonds and the number of lone pairs, because the lone pairs have to only go into hybrid orbitals. Okay. So we'll do another one of those. We'll do another one of these examples as we go through here. And now we're going to talk about expanded octets here in a moment. Okay. Now, before I do this, I just want to talk a little bit about this chart and take a step back and say, okay, is Vesper theory consistent with hybridization? I mean, it better be. But why in Vesper theory did we only count a multiple bond as one pair of electrons? Why did we ignore the other two bonds? And it's a very straightforward answer. The geometry of the molecule, the geometry around this central atom, is based on the hybrid orbitals only. That's it. Well, what goes into the hybrid orbitals? Well, the hybrid orbitals are what are used to form the sigma bonds. And if they're not formed the sigma bond, what's in them? The lone pairs. So Vesper theory, when we say ignore the multiple bonds, what we're saying is the pi bonds don't determine the geometry. Only the sigma bonds and the lone pairs do. So that's why everything is consistent here. Okay? So hopefully that makes sense. Okay, now, expanded octets. In the periodic table, if you are at basically row 3 or lower, you can form an expanded octet. And that means that you can share either 10 to 12 electrons, and you're not bound by the octet rule. Why? Why does it have to be row 3 or lower? Why is it basically a mortal sin to draw 5 bonds to a carbon? Because carbon can't form an expanded octet, but why not? So it all has to do with hybridization. So let me take, for instance, this molecule. Let's do PCl3. So PCl3 would have a phosphorus with its 3 Lewis dot structure, with its 5 valence electrons, And I'm going to put the chlorines in because the chlorine's unpaired electron would be used to form the sigma bond with each of the three phosphoruses. Okay. Now, PCl3, in terms of this geometry, that phosphorus what would be the phosphorus's hybridization? And the video is going to stop and you're going to choose. Okay, if you said that hybridization, because there are 3 sigma bonds and 1 lone pair, that means there are 4 hybrid orbitals, and that is sp3. So it's sp3 hybridized. Great. But what does that have to do with expanded octets? Let's expand the octet. Let's expand the octet by taking that phosphorus that already has 3 chlorines attached to it. And now let's take each one of these electrons in the lone pair, and let's add 2 more chlorines to it. And now let's make PCl5. Legit structure? Yes, it's legitimate. Because phosphorus is row 3 or lower on the periodic table. Our periodic table would second row would go CNOF. Underneath nitrogen is phosphorus. Underneath oxygen is sulfur, which we'll get to in a minute. And then under fluorine would be chlorine. So this is row 3, this is row 2. So phosphorus is perfectly allowed to have, in this case, 2, 4, 6, 8, 10. It would have 10 electrons. What is its hybridization? Well, let me ask the question a little bit differently. What is its VSEPR geometry? What is the VSEPR geometry of that phosphorus? Okay, the video is going to stop in a moment, and you're going to choose that answer. Okay, so hopefully you said because it has 5 valence sets of 5 sets of electrons around the phosphorus, that it would be trigonal bipyramidal. That would be trigonal bipyramidal. What hybridization does it have? All right. Phosphorus, the valence shell, or the largest quantum number, principal quantum number, would be 3. So phosphorus would look like this. That would be how the 5 valence electrons in phosphorus are arranged in the ground state. Obviously, we have a problem like with carbon. I need to form PCl5, so I need to take this electron and I need to promote it up. The question is, to what? Now, what is directly above the 3p orbital? If you said the 4s orbital, you are correct. What is above the 4s orbital? The 3d orbital, the 5 3d orbitals. Here's the problem. The problem is the quantum mechanical rules of hybridization only allow you to hybridize orbitals with the same principal quantum number. You cannot hybridize a 3 and a 4. You can only hybridize 3s. So this paired electron, if I'm going to unpair it, I'm going to need to have enough energy to get it to the 3D. So if this is the ground state, then the excited state would look like this. Now I have 5 unpaired electrons. You might say, but wait, isn't that going to cost me more energy? Yes, it is. What am I going to get back for that energy that I spent? You're going to be able to hybridize the atoms or hybridize the orbitals, and you're going to get stronger bonds. So, and the only way to do that is to be able to mix the orbitals together, and the quantum mechanical rules say you can't mix 3s and 4s. So you're going to have to pay the price for that, but you're going to get it back when you form stronger bonds from the hybrid orbitals. Great. All right, so hopefully you're with me at this point. So now what am I going to do? Now I'm going to say, you know what? I'm going to mix these orbitals. And here's the thing. I'm going to mix the 3s, the 3p orbitals, and 1 3d orbital. That's a total of 1 3s, 3, 1. That means I'm going to get 5 hybrid orbitals. Okay, so I'm going to get 5 hybrid orbitals. 1, 2, 3, 4, 5. What am I going to call them? I'm going to call them dsp3. You can call them sp3d. I don't honestly care. Although I think technically D should come first, but it doesn't matter to me. Each one of those dsp3 hybrid orbitals is going to have 1 electron in it. Now, this is the critical part. I mix the orbitals first, then I put the electrons into it. What does a dsp3 hybrid orbital look like? No, it looks like this. How many of them are there? 5. 5. So what is the geometry? Trigonal bipyramidal. So each one of these is going to be a dsp3 hybrid orbital for phosphorus. Each one of them is going to contain 1 electron. And so what am I going to do? I'm now going to overlap the chlorines, and I'm going to form my PCl5. Now, the only thing tricky about this is what's the hybridization, or what is the geometry and hybridization of that chlorine? It's sp3 because it's got 3 lone pairs plus a sigma bond. That means there's 4 sp3 hybridized orbitals. It's tetrahedral. So my phosphorus down here, my chlorine would have a tetrahedral geometry with 2 electrons in each of the 3 orbitals. This is an sp3 hybrid orbital. This is a dsp3 hybrid orbital, and I'm going to overlap each one of those to form the sigma bond. And do that 4 more times and you have PCl5. Okay. So we added energy to go from the ground state to the excited state. We had to skip the 4s orbital and go to the 3d. We then mixed those together to form 5 dsp3 hybrid orbitals, which, because there were 5 hybrid orbitals, it is trigonal bipyramidal. Okay. Now, the big question. So let's take a step back, take a breath. Okay. Why does the atoms that can form expanded octets, why do they need to be in row 3 or lower? The answer? Because only row 3 or lower has this d orbital that we can expand into and hybridize. There's no 2d orbital for carbon. And you're not allowed to hybridize orbitals of mixed principal quantum numbers. So anything that's row 2 or lower does not have a 2d. Only row 3 do you now have access to the d orbitals. So that's why it's row 3 or lower to form the expanded octets, because you need the 3d orbital. Or then 4d or 5d, whatever. But the first d orbital is the 3d. So that gives us dsp3. Okay. All right, d2sp3. I'm going to need sulfur for this. So I'm going to take sulfur and I'm going to put, I'll just make it up. I'll put 4 fluorines around the, or I'll put 6 fluorines around the sulfur. What does that mean? I started with this Lewis dot structure. And so there's my 6 fluorines attached to the sulfur. What's it look like in the orbital picture? What it looks like in the orbital picture is the following. Sulfur is row 3. Again, CNOFPS. So sulfur has the 3s, the 3p. So it looks like that. Again, skipping over the 4s into the 3d. That means that if I want to form SF6, I need to promote 2 electrons up. So ground state into (3D). So now I end up with my 6 unpaired electrons. I'm now going to mix the S, the 3 Ps, and 2 Ds. I'm going to get 6 hybrid orbitals that will be called D2sp3 or sp3d2, either one. Critical part is I get 6 hybrid orbitals. what should the geometry around that sulfur be with 6 hybrid orbitals? Octahedral. I always mix orbitals first. Then for sulfur, 1 electron in each hybrid orbital. So there's my D2sp3, each containing 1 electron. Now fluorine. Fluorine is also sp3 hybridized. So if I have my fluorine, I would have it being tetrahedral in its electron pair geometry. And there's my sigma bond. And so if you do that 5 more times, you've got SF6. So this is how we handle expanded octets. And also this is the process by which we undergo drawing an orbital picture. And there are practice problems on drawing orbital pictures that you can try. There's also an online quiz where you're going to draw out an orbital picture and then you're going to upload it to Canvas for grading. Okay. So this is really the first organic topic about how we form carbon bonds, but it's also the underlying reason. Hybridization is the underlying reason of how we have that row 3 or lower to form expanded octets rule from general chemistry. Okay. Okay. Just a couple quick points. We'll get into intermolecular forces and then that'll be the end of this video. Free rotation around sigma bonds. What does that mean? Well, if you had a carbon, if you had this ethane molecule, which is a 2-carbon with carbon-carbon sigma bonds or single bonds. If I had this picture and I have this as my sigma bond, there basically is quote-unquote free rotation around that sigma bond. And what that means is that I could rotate if I put each one of those carbons into a tetrahedral representation with, again, these are towards you, bold wedges are towards you. This is a bold wedge, and a dashed wedge is basically away or behind the screen. I have essentially free rotation around that carbon-carbon bond so that I could rotate the hydrogens basically in 360 degrees. Now, the rotation is not free, as we're going to find out in a couple of lectures, but the energy that it would take to do that, there's more than enough kinetic energy at room temperature because of the idea that we're not at absolute zero in order to do that. So what that means for a Lewis-Dot structure is the following. That if you had, for instance, this Lewis-Dot structure, and you wanted to think of this in terms of maybe rotating groups, this structure is the same as having the CH3 group up here, or having the CH3 group down here. All three of those are exactly the same Lewis dot structure. And so you can kind of think of that as I have the ability to rotate one of these groups. I have the ability to rotate those groups into each other. And we'll talk more about that as we get into three-dimensional structures of alkanes in an upcoming lecture. Okay. But I'm just going to throw it out there. All three of these are exactly the same molecule. However, there is not free rotation around a carbon-carbon double bond. And if this is my sigma bond, and then I form my pi bond, and if I was looking at this head on, again, these bold wedges mean that the molecule is pointing towards you, that these hydrogens are pointing away from you. So basically, I'm looking at this molecule as if it was pointing towards you, and then these guys were like pointing away from you in the back. So in other words, the plane of the molecule looks like that. There is no free rotation around a double bond. In other words, at room temperature, there's not sufficient energy to rotate. Let's say if I had a CH3 group, if I had a carbon with 3 hydrogens attached here, and I had them basically one bold and one dashed. This is not the same structure as having the two CH3 groups on the same type of wedge. These two are not equivalent. The amount of energy that it would take to convert one into the other is not, that energy is not available at room temperature. In the case of the carbon-carbon sigma bond only, room temperature, there's more than enough energy to do that rotation. But when you have a double bond, what you actually have to do is you would have to break the pi bond and then rotate. And to break the pi bond is far more energy than what's at room temperature. So this is going to lead us to what we call stereochemical isomers. But just be aware that there is no free rotation around a double bond. Okay. And that there's more explanation about that, and we'll build on that, but it's just something that's in Top Hat. So that leads us to some discussion, just a quick discussion about isomers. And so what are isomers? Isomers are basically molecules that have the same molecular formula, but they have different structures. And structures can mean a number of things. So let's say, for instance, that I have a molecule that has 2 carbons, 6 hydrogens, and 1 oxygen. How can I construct that molecule? Well, I could have my carbon, the 2 carbons together, and I could add the oxygen and hydrogens this way to make ethyl alcohol, ethanol, or I could construct those atoms like this to form what's called methyl ether. And these are two totally different molecules. Ethanol is a liquid at room temperature. Methyl ether would be a gas at room temperature. One, depending on your age, you can consume legally. This one would probably, with a flame, they both with a flame would burn, one more explosively than another. These are two completely different molecules. So constitutional isomers, the constitutional part means that the atoms are attached differently. They're attached in different structures, but yet they have the same molecular formula. Now, stereoisomers are molecules that are the same constitutional isomer. So the atoms are attached the same way, but they have different three-dimensional structures. And the example that I just gave you, where if you had, for instance, and I'm going to look at this alkane now, or alkene, which we'll get to in naming it, this carbon-carbon double bond, these two molecules are different in the respect that they have different three-dimensional structures. The atoms are attached exactly the same. In other words, there's a methyl group attached to a carbon of a double bond attached to another carbon of a double bond attached to a methyl group. That's the same in both structures. But having the two methyl groups on one side of the double bond versus having them on opposite sides of the double bond is different three-dimensional structures. And so that gives us the idea of stereoisomers. The same constitutional isomer, but having three different three-dimensional structures. And as we saw, these two structures cannot be interconverted into each other because you'd have to break the pi bond first. Just so you know, constitutional isomer can also be called structural isomers, and I actually like the term structural isomer better than constitutional isomer. It doesn't matter either here. It's neither here nor there, but both of those terms represent then the connection of the atoms to form different structures. But a stereoisomer has the same. They're the same constitutional isomer, just different three-dimensional structures, and we'll expand on this more and more in upcoming lectures. Okay, now the final topic is to lead us into the idea of intermolecular forces. So in order to determine whether molecules undergo dispersion or dipole-dipole or hydrogen bonding, intermolecular forces, we needed to determine Lewis dot structure, VSEPR geometry, and once we have that, now we have to determine polarity and whether a molecule is polar or not. So just remember, electronegativity is the ability of an atom to attract electrons to itself in a bond. Fluorine has the maximum number, which is 4. The dipole moment is a measure of the polarity of a bond. So if you had a carbon attached to a fluorine, the fluorine being more electronegative than any other element on the periodic table, including chlorine, would pull electron density towards itself and leave the carbon slightly positive and giving the carbon then being slightly negative as it pulls that electron density from the carbon. This is still a covalent bond, but this would now be what we would call a very highly polar covalent bond, but it is still sharing. And our delta plus and delta minus terms mean carbon would have a little bit of positive charge because it has some electron density lost to the fluorine. Okay, so for every bond we can determine whether or not it's a polar covalent bond, showing which atoms are getting electron density and which ones are losing. So we can use delta plus, delta minus, or we can use this arrow. And I usually put the plus at the end of the arrow to indicate where the plus and minus ends of that arrow would be. So that's sort of a vector that tells us the direction of electron sharing when it is unequal. Okay. So is a molecule polar or not polar? We'll get to that in a minute, but if you have a polar molecule, so you have, for instance, maybe a hydrogen and a chlorine. The chlorine being more electronegative than hydrogen is going to pull electron density away from it, being delta plus and delta minus. How we know that a molecule is polar and how polar it is by putting it inside of an electric field and just seeing how quick or how well the molecules orient themselves. So for instance, when we put these in an electric field where there'd be two different charged plates, the HCl molecule is just kind of randomly oriented. But when you put a negative charge on one plate and a positive charge on the other, the delta positive parts of the molecule are attracted to the delta minus. The delta minus would be attracted to the other delta positives, and so the delta minus would be attracted to the positive. So the molecules line up, and that's how we can tell actually if a molecule is polar or not and how polar it is. And its overall polarity of the molecules measured in what is called the dipole moment. And I don't want to get too much into that because we're going to use bits and pieces of this for explaining organic molecules. So a molecular dipole moment then is sort of a vector sum of all the dipole moments. Now I'll get to what that means in a moment. For a molecule to be classified as polar, these are the two criteria that you need. Number one, it has to contain a polar covalent bond. If it only has relatively nonpolar covalent bonds, or if it has perfectly covalent bonds, it won't be polar. It needs a polar covalent bond. And secondly, it must have a non-zero molecular dipole moment. Now, what does that mean? Let's look at an example of that. So here's water. And I love water as my trick question that I can sometimes ask freshmen when they're taking general chemistry, and not all freshmen, or not all general chemistry students are freshmen, but I'll ask them this question. I'll say, water, I've drawn its Lewis dot structure. Is it polar or is it nonpolar? As a matter of fact, let me ask you that question. The video is going to stop, and you can tell me whether it's polar or nonpolar. And what did you say? Did you say it's polar or nonpolar? Hopefully you said it is polar, because in what universe is water nonpolar? But if I drew the Lewis dot structure like this, what would I do? Well, I would say the oxygen is slightly negative, the hydrogen is slightly positive, so I would be drawing a vector this way, and then I would be drawing a dipole moment that way. And what we do to determine whether a molecule is polar or not is to see whether those two cancel each other out. If they don't cancel each other out, then the molecule's polar. If they do cancel each other out, then it's nonpolar, is basically the essence of this. So when I draw the Lewis dot structure of water like this, I can normally get a good chunk of general chemistry students to say water is not polar. And then I'll say, but wait, you just told me that water is not polar. And they're like, well, water is polar. When you're looking at the Lewis dot structure, what do we need to do? We need to put it in terms of the VSEPR geometry. So when I look at that oxygen, what is its electron pair geometry? Oh, that'd be another good question to ask you with the videotape, but if it's stopped, but I'm not going to do that right at the moment. It's tetrahedral, right? Now, when you're drawing a molecular dipole moment, you ignore the lone pairs. So in this case, how would the bond dipoles go? They would look like that. Are they canceling? No. And the net dipole moment would look like this, right? That means this part of the molecule would be slightly negative. This part of the molecule would be slightly positive. Why? Because that's the overall vector sum of the dipole moments. And this slide goes through some of the ways that you could basically start and end and determine what the overall dipole moment is. I'm going to make this a little bit simpler by saying if those dipole moments don't cancel, the molecule's polar. If they do, it's nonpolar. Now remember that you needed to have polar covalent bonds to begin with. So all these structures have to be put in their VSEPR theory or into their VSEPR geometry. If they're not in their VSEPR geometry, you could end up telling me that water is nonpolar. And hopefully nobody did that. So just in terms of the kinds of geometries that you'll see, here's BF3. BF3 is definitely has polar covalent bonds, right? The fluorine would be slightly negative, the boron would be slightly positive in each one of these cases. So it's got 3 polar covalent bonds. But does it have a net dipole moment? Well, whenever you have a symmetrical molecule, and this would be trigonal planar in its geometry. In the trigonal planar geometry, when you have the bond dipoles and the molecule's symmetric, they're going to cancel each other out. So BF3 is a non-polar molecule. Another example of a non-polar molecule would be methane, for 2 reasons. Methane is nonpolar because we treat a carbon-hydrogen bond as if it is a relatively nonpolar covalent bond. So just having a molecule with carbon-hydrogen bonds is not sufficient to become polar. So it fails rule number 1. On the other hand, let's substitute 4 chlorines for the hydrogens and ask the question. This is CCl4, which is called carbon tetrachloride. Is carbon tetrachloride polar? Oh, wait. In the molecule that I just gave you, it would be, but that's not carbon tetrachloride. I usually say if this is a high-class operation, I would have removed that part from the videotape, but I'm going to be honest. Seeing me make these little mistakes is hopefully you see that when you make you'll make them too. Maybe I should remove that from the video, but I won't. Carbon tetrachloride, is it polar or nonpolar? Well, again, in a tetrahedron, if it's perfectly symmetrical, as it is, all 4 of those will cancel. So it will have no dipole moment, and the reason is because all of those bond dipoles cancel each other out. So in a symmetrical molecule, when you have the same thing attached in all of the positions, they will cancel each other out. You'll have no dipole moment, and you will have a nonpolar molecule. And indeed, carbon tetrachloride is a nonpolar molecule. it was used as a dry cleaning fluid, so that it being nonpolar would be attracted to the grease molecules, and so it was used as a dry cleaning. Also, it has a low boiling point, and we'll get into that in the next lecture. So carbon tetrachloride is a nonpolar molecule. I'll give you one more. Carbon dioxide. Carbon dioxide would have this Lewis dot structure. Is carbon dioxide polar or nonpolar? Okay, the video is going to stop. You're going to give me your answer and then come back. Carbon dioxide would have a linear geometry, and its bond dipoles cancel. Again, it's symmetrical, so carbon dioxide is also nonpolar. Okay. So basically, when you're looking at a geometry, if that geometry is symmetrical and has the same atoms attached in each of the positions, it will be nonpolar as they cancel each other out. If it's not symmetrical in general, it will be polar. So we'll take a look at a couple more. Water is definitely polar. Again, I'm showing you the bent geometry here of the bent molecular geometry. Remember, there'd be lone pairs. And the interesting thing in determining molecular polarity is that the lone pairs don't play a direct role. There's no vector that you drew, although some general chemistry books do draw vectors to lone pairs. It's not correct to do that. So water actually, you would not draw vectors to the lone pairs, and it would be polar. Now, lone pairs do play a role because they create the VSEPR geometry that you're using to determine the individual bond dipoles and whether or not they're canceling. So lone pairs do play a role, but it's not direct. It's indirect in affecting the structure. So there's water. There's ammonia, which has got a pyramidal molecular geometry, but the lone pairs are where this arrow is. That would be the direction of the dipole moment, where, again, your delta minus charge would be around the nitrogen and your delta positive charge would be around the hydrogens. And so ammonia, because it's not symmetrical, because it's got the lone pair here, it is tetrahedral, but it's not symmetrical. It would be polar because it's not symmetrical. HBr, pretty simple. You'll see these diagrams in your book. Red is delta minus, blue is delta positive. So this is HBr, which would be definitely polar. Here's CF2. CF2 has 2 fluorines and 2 hydrogens. It's tetrahedral. Since the same atoms are not attached in those 4 positions, it would be polar, with the area around the fluorines being delta minus and the areas around the hydrogens being delta positive. And let me come back here for one more moment, and then this will end this video. What does it mean to be a polar molecule? What it means to be a polar molecule is this. You need to have in your shape, you need to have some area that is delta minus, and you need to have another area that is delta positive. If you have in your shape all the same delta minus charge, you are not going to be polar. You need to have that difference in, I would say charge, but that's not correct. You need to have a difference in electron density so that you have, and then charge I guess is okay. what you need to have is a delta minus and a delta positive ends of the molecule, because that's what's going to make you polar. The fact that you do have that charge differential. And in intermolecular forces, it's going to be the delta plus charge that's going to be attracted to the delta minus end of other molecules, and delta minus to the delta positive end of others as well. So a polar molecule then has this the surface has a difference in charge. A nonpolar molecule has no difference in charge. And it doesn't matter if it's all the same negative charge, it's the difference that is important. And so we'll pick this up as we finish off intermolecular forces in the next lecture video.